Hello everyone, welcome. Let's solve a classic invert a binary tree. We're given the root of a binary tree and we want to invert the tree and return its roots. And when you look at a tree structure, the way it is in computer science, we do have an already inverted tree, in which case the root is what we have at the top and the branches and leaves beneath. That's an inversion of a real life tree. But in computer science, when we are asked to invert a tree, we are basically just asked to swap the left and right child, as we can see here. This is our original tree. The left child is 2, but on the inverted side, the right child is 2, and the right child here is now the left child in the inverted tree, and we're also going to invert its children too. Basically, this is what we are expected to do. So I think that this is such a great question to practice your post order depth first search and also recursion. So let's jump right into it. So we're given a tree with the roots 4 and it has all of these branches, and we can already see that when we are asked to invert, it basically means that swap their children such that 2 is on the other side and 7 is swapped from where it's supposed to be, and we're going to traverse the children and basically do the same for its kids and just invert them. So how do we go about this? So the first thing I want to do is that we want to traverse the entire depth of the tree. We can also run a breadth first search where we are going in order traversal and just switching them as we go along. Or we could also run a depth first search like we'll be doing in this code, where we traverse the depth of a tree. We'll use the post order traversal. We traverse the left child, the right child, and then the root. Now let's go to the depth of the tree. Now we're going to traverse left, right, and then root. So we're traversing the entire left child of the tree, right? And then we go to the last child, which is a leaf node. We see that it's a leaf node, it has no left or right child, so we just go ahead and go back to its parents. But before we do anything about its parents, we have to check its right child. Is he a leaf node? Does he have any children that we can swap? It doesn't, as we can see, so we can just go ahead and go to the root. And just like how we swap numbers, if you are given two variables 2, 3 and you want to swap them, what you are going to do is to have a third variable, temporary variable, that stores the value of 2, for instance, and then you can assign 3 to 2, or you can assign 2 to 3 and 3 to this temporary variable. There has to be a container that holds what we had previously, so we don't completely lose access to what we are storing. This just means that when we want to swap the left child and the right child, which we know that is as easy as changing the edges pointer, these are edges, right? So swapping the children is going to be as easy as we're going to check the left child, the right child, and then go over to the root parent, and then we're going to swap its edges such that its right child now points to its left child and its left child points to the right child. And we're going to easily do that by storing a reference to one of those children so that we don't lose access to it. What I mean is that if we have to set the right child, that is okay, the right child is 3, we have to set 3 to 1. Then what do we set 1 to? We can no longer set 1 to 3 because we already assigned 3 to 1, thereby losing 3 forever. So we need a temporary variable to store 3. So when we store 3 to 1, 3 is no longer 3, 3 is now 1. Then we can now go ahead and store the temporary variable that now contains 3 to 1. And now that this has been swapped, this left subtree has been swapped and sorted. Let's kind of like clear this up so it's not looking all that rough. If this subtree has been sorted, then we go over to the root node, but we cannot yet traverse the root node because remember we're doing the post order traversal, left child, right child, and then the root. So we're traversing all of the left subtree, then we go over to the right subtree, and we are going to follow the same order where we traverse down each subtree. But fortunately for us, the subtree ends just here. If it adds more depth, we have to traverse down, and that's why we're using a depth first search, because the tree can be as high. We don't know the number of inputs that we can be given, but we have to assume that we'll be given any number of inputs, right? And so we traverse down the left child of this tree. We can see that there is no children, this left child has no subtree, it's a leaf node. We traverse to the right, no subtree is a leaf node. So we go over to the parent and then swap the pointers such that 7 now points to 9 on the left child and 6 on the right child. And now that this has been swapped, so this will have 2 pointing to 3 and 1, 7 pointing to 9 and 6. Then we can now go over to the root node and then just easily swap the pointers such that this is now the left child and this is the right child. And because all of the children under this have been traversed and swapped, we no longer need to bother, because so that whatever is under this has already been swapped. That is the exact logic that we're going to follow when writing the code. Let's jump into the code quickly. So first we want to cover our base case as with any recursive solution. And our base case is going to be that if we are not given any root, then we just want to return the root. If our root is null, basically, then we don't have any reason to traverse the tree, so we'll just return the root, the empty root that we're given. Then we want to swap the nodes, the root values. So first I'm going to create a temporary variable that stores the left child. Then I'm going to store the right child of the current root we are on to the left child. So basically I'm storing the right to the left, and then I'm going to go ahead and store the left into the right. So the left is going to be the temporary variable. It's already stored, we are storing it in the temporary variable, and that's what I'm storing in the right. If I had not stored it here, then would have lost this value here. I'll just be storing root right to root right again, since root left on this line is now root to right. Then after we've done this, we want to traverse down the tree, because recall I want to traverse the left tree. When we traverse the left subtree, we're basically going to be swapping its left and right child at every point that it has this. But if it doesn't have a left child, then that means it's a leaf node and to just return the leaf node. But if it does have a left and right child, it's going to swap it. Now after we've swapped the children on the left child, we want to go ahead and swap the children on the right subtree too. And then after this is done, we just go ahead and return the root. The time complexity is going to be a linear time because we are traversing the entire tree depth. And the space complexity, okay, I didn't put self. And the space complexity is also linear since we are using the recursive data structure. And we know that when using recursion, it stores all of the processed input on the computer's call stack. So that extra memory that is being used is going to be linear. So let's submit this and see what we get. This runs pretty fine. So let's take a look quickly at our JavaScript code, which is basically going to be the same thing as the Python code. I say this all the time, but the only difference is the syntax. If we don't have the root, then want to return the root. If it's a leaf node, just go ahead and return it. Then we want to swap the entire left child and right child, and then we want to traverse the depth of the right tree and the depth of the left tree and just return the root. The entire explanation concept that we've explained for the Python and the code walkthrough, but different syntaxes. So in case you are jumping over to JavaScript code, I don't explain it here. I already explained it in the earlier minutes. The time complexity and the space complexity is the same, linear. And yeah, that's about it. Thank you so much for watching. I'll see you in the next video.